8.6, Natural Logarithms. This is the final section we'll be doing in Chapter 8. We'll be focusing on the first objective, evaluating natural logarithmic expressions. We've done a lot in this chapter. We've done logs, we've done evaluating exponential equations, and now we'll be looking at the natural logs. All right. First thing I want you to know is that y equals e to the x has an inverse, which is known as the natural logarithmic function. So if you see y equal to the ex, this is the first graph, graph 1. I just said graphed. The first graph. And then your inverse is going to be y equals ln x. So it is a flip over that y equals x axis, or y equals x line, I should say. Okay, let's go ahead and look at example 1. Simplifying natural logarithms. This is back in 8.4 when I said we'll be using this later down the road. These have the same exact properties as the logs. That makes it nice and easy because you don't have to learn anything new. It's all consistent. If you are dividing, it's quotient. If you have that power and it's going out front, you know it's power. If you're adding, it's multiplying. Okay? So looking at this one here, 2 ln 12 minus ln 9. Now you want to make sure that that is in ln, in lowercase l, and why it's ln and not nl. I'm sure it has something to do with the English translation of that. It's probably logarithmic natural or something like that, but I haven't Googled it, so. All right. Writing this as a single, that's one single natural logarithm, so we should have 1 ln something. Okay, so we've got this 2, and it's going to come here, and that's going to be the power. That gives us ln 12 squared minus ln 9. You can evaluate that if you wanted to, but it's not really needed because it just says write it as a single natural log. This means to divide. So now we have ln 12 squared over 9. Now if we were to simplify this, it would be ln 144 divided by 9. And we can actually take this down one more time because 9 goes into 144, right? Because 1 plus 4 is 5, 5 plus 4 is 9. This would give us ln of 16. Okay, if you give me this, we are good because that's what it asked you to do. Write it as a single natural logarithm. It did not say in simplest form. This would be in simplest form. So if it does ask for that, then you have to do this. Okay, example 2. This one is a word problem, and it's not hard. It's just plug and chug for the most part. Find the velocity of a spacecraft whose booster rocket has a mass ratio of 22, an exhaust velocity of 2.3, and a firing time of 50 seconds. Can the spacecraft achieve a stable orbit 300 kilometers above Earth? And I want to say that up in this equation up here, it tells you what you have to have to sustain that. Here we go. A spacecraft can attain a stable orbit 300 kilometers above Earth if it reaches a velocity of 7.7. So we would have to have 7.7 or greater, right? So I'm going to put that down here. And I'm going to write it out so greater than 7.7. Okay. Okay, it tells us what all those things mean. The T, okay, should have just gone over this one all together. All right, where is it? Okay, the velocity of the exhaust is C. The ratio is R, and the T is time. So C is your exhaust, R is your ratio, and T is the time. So T is 50, and I do believe it said in seconds. We'll double check that. Yeah. Right? And we have C is the exhaust velocity, which is 2.3, and then the R is the mass ratio, which is 22. So now all this is a matter of substitution, a simple matter of substitution and simplification. So we're going to have V equals negative 0.0098 times 50 plus 2.3 natural log of 22. And I'm going to go ahead and use the calculator. Again, using the graphing calculator only because it's what's right there readily available. So you've got negative 0.0098 times 50 plus 2.3 times ln is right here, and that's 22. And we have 6.62, right? So 6.62. So would we be able to achieve a stable orbit? No, because 6.6 is less than 7.7. Okay, all right, so that's it for the first objective. We're going to go ahead and stop this one, and we'll see you later.